She's one of the leading understanding of the structure of our universe and galaxy formation and evolution. She's won a number of awards, including the National Academy of Sciences member, Sloan Fellowship, the Gruber Prize in Cosmology. She won the National Medal of Science from President Obama. Since she became emeritus, she's led a number of additional initiatives, including the Osterbrock Leadership Fellowship Program for graduate students, both at our university and other universities. And then she's the founding director of the Earth Futures Institute, starting in 2019. I'm sure she'll be telling us a lot about that today. So, Sandy, it's great to have you here.
Thanks very much. Really appreciate that brief introduction. Let me make a confession here. I'm completely terrified at giving this talk than any previous talk. I'm talking about something that I'm not trained in. It's a vast subject. I have only a superficial acquaintance of it. And furthermore, some of the things I'm going to say are not exactly pleasant, and how to phrase those in a way that's positive. This is my first experience with that. So I hope you'll all cut me a little bit of slack on this. Now, I've emphasized that this is a new subject for me, and I'd like to start this talk by acknowledging some people, great thinkers, I think, whom I have learned from. I won't go through the whole long list, but I want to highlight especially the name at the bottom, Richard Nolthenius, who is a great local asset, professor of astronomy at Cabrillo College, who has been thinking about these matters far longer than I have, and first brought these issues to my attention. Thank you, Richard. Okay, let's look at the major points of this talk. I'm not going to read this slide. This, unfortunately, is like a lot of my slides. I have almost deliberately, but despite myself, despite my better intentions, violated my main rule for giving talks, which is one idea per slide, right? And the problem is that the subject is too big. And therefore, what I've done is adopted a different strategy. The slide deck will be available. You can go back and consult the details. You can look at the graphs. You can borrow the graphs, et cetera, et cetera. And so what I've done is divide the talk into chapters. And at the beginning of every chapter, there are a bunch of summary points, which I will go through. And then the slides in that chapter sort of just back that up. And we're going to go through them rather rapidly. Okay, so major points here. Energy is the engine of the economy, and it has been accompanied by economic growth. Economic growth has historically required more energy. Oil is very special. When oil goes away, life as we know it is going to be very different. Then I want to talk about the so-called transition to renewable energy sources. Do I think that this is actually happening? And the answer is no. And unfortunately, that's bad because it's lulling us into a false sense of security. Somehow we think that people out there are doing good things and that modern life that we know it can continue, fueled by magical energy sources that have no detrimental environmental impact. And universities and their research programs are complicit in this. The problem with that is if even we solve the energy problem, we would still have a massive economic enterprise, and many other aspects of that enterprise are impacting the environment detrimentally, and they will continue unabated even if the energy problem could be solved. So one of two scenarios seems likely. We continue to have cheap oil and coal, and we're going to burn them, and that's going to create severe global warming. Alternatively, these items will begin to dwindle soon, which will help the climate. But because of my argument here about the close correspondence between the economy and the availability of energy, there's going to be economic dislocations and disruptions that I think could be extremely painful. Either way, society over coming decades could look very, very different. And if I still have time in this very long talk, I want to talk about the role of astronomers, because I think astronomers are very special. Okay, chapter 1, The criticality of cheap energy to modernity. Energy is critical to modern life and the economy, but it is woefully underpriced. So let's explore that. Here's a chart that shows GDP versus energy consumption for countries. Beautiful correlation with a log-log slope of almost 1.95. Historically, over the last few decades, energy has grown as the GDP has grown, and they're almost linear, but there's an energy efficiency improvement of about 1.3% per year. We are getting slightly more efficient. From year to year, you can even see fluctuations in the GDP and the energy consumption. So even the residuals are correlated. All right, so if you remember one thing in this talk, I'd like it to be the next 3 slides. So let's bring this home. How much energy are we talking about? In your gas tank, there are 1.2 billion joules of energy. What the hell does that mean? You know, I have no idea. I don't even really know what 330 kilowatt hours means. Let's bring it down to something we really understand. How many years of human labor for somebody working flat out sustainably for 8 hours a day? How many years of human labor is it? Or is it just weeks? Is it days, weeks, centuries? What is it? Do you even have any idea? I did not. You do, because Sven is part of this community, but most people have no idea. The answer is, it's 5. Okay, which struck me as a lot when I first learned that. Wow, 5 years of human labor in my gas tank. That's not the point, though. The point is the next points, okay? What did that gas cost? Order of magnitude, we're astronomers here, $50. What do 5 human years of labor cost if you pay somebody decently with benefits, et cetera, $500,000? The bottom line is that the energy we're using today is underpriced by a factor of 10,000 compared to the energy that humans grew up with before they found fossil fuels. So what you need to do is in your daily life, when you take a shower, when you drive the car, you need to reflect on the implications of that underpricing, because our economy, our economic system is based on prices, and it allocates things according to prices. And this is a gigantic historical price mismatch. And that at bottom is why we're in the fix we're in today, this underpricing. Okay, so it inspires you to take a new look at previous civilizations with the realization that they were vastly energy poor compared to us. We are not smarter. We are not even more enlightened. We are not more social justice oriented or any of those things. No, we have the benefit of just having cheap oil and coal. So please, if you remember one thing, remember this mispricing and its consequences. I'm going to take a little detour here just to explore some bigger issues before I get back to my main theme. Well, evidently I'm not getting I'll take that detour in a bit. Okay, so chapter 2, fossil fuels are everywhere, wide applications. We don't often think about this, feedstocks for industrial products. And look around your office or kitchen and observe that the creation of every single item there relied on fossil fuels. Okay, so here's a history. This is total world energy consumption in recent years, and you can see how special this time is. A word here about wind and solar. They're contributing about 6% of global energy use now and growing slowly. The overall use is growing. Wind and solar are accounting for somewhere between 1/2 and 3/4 of that growth. So they're important, they're providing the extras, but numerically they are small. And in order to take over the majority of energy use, they would have to grow enormously. Now here is a different graph of fossil fuel emissions. And what I want to focus on actually is where those emissions are spent. So let's enlarge that. And I call your attention to certain sectors here. So here's transportation, which is mainly oil. It's like 22%, but there's more transportation in here, mining and agricultural vehicles. And when you take them and add to that, vehicles together are about a third. And then there's electricity, which is about 40%. And then everything that's left is industrial uses, sometimes industrial heat or feedstocks. So trying to simplify, oversimplifying greatly, 1/3 is transportation and vehicles, mainly oil. 1/3 is electricity, mainly coal and natural gas. And the last third is these feedstocks, heat, and commercial and residential heat, which is mixed oil and coal. Okay, so now there's some conclusions. Converting to electric vehicles would solve only 1/3 of the CO2 problem. And converting to electric vehicles, as I will show you, requires roughly doubling the power capacity of the current electricity grid. So that's a very big job. The last third, looking ahead, that is to say the industrial feedstock problem, poses problems with no known solution. This problem has many pieces. Don't think that electric vehicles somehow solve the problem. They're actually a small part of the total. How much oil and coal are left? Sorry, I'm not going to engage in questions because I'm not going to get through the talk. Painfully, I have to say no. Okay, how much oil and coal are left? It's hard to tell. Opinions differ. A common statement is that we burned through about half of the oil. Actually, though, coal may be a worse threat because many people say that there are centuries left of coal to burn. So think about that in the context of global warming. A conservative estimate is that we will continue burning oil and gas at current levels through at least 2050. In other words, people who know the economy and know the supplies are telling us there's no net zero by 2050. And I'm going to return to that theme later. So here is a history of US petroleum production. We peaked around 1970. We were going down. I was a young person at that time. I think our leaders were worried and panicking and didn't know what to do because we were importing a lot of oil from the OPEC countries. But then a miracle occurred. And this man in Texas figured out how to get oil out of rock. And that's what we call tight oil or the shale revolution. So here are the shale installations in the United States. These here in Appalachia produce mainly natural gas. These produce both oil and gas. So here's a history of the oil production from the oil producing shale plays. Well, I guess it's everything here. Okay, they're peaking.
Could somebody click OK?
Yeah, I don't see it on my screen, unfortunately. That's a good point. Let's take some time out. I'll get out of the, go to Zoom.
You drag, oh yeah, drag your mouse up.
I can look.
Yeah.
Thank you. That's right. I was blocking important words, wasn't I? All right, now what? Problem is I don't see my cursor on this thing.
It's in the middle. It's just right in the middle.
Bring it back.
Keep going. PowerPoint. No, you don't show. I'm gonna go Zoom.
Do I?
That one, yes.
Why do I want to be there?
So we want
Reshare. There. Rescued. Thank you. Okay. Point is that some people looking at these data, when they see flattenings out like this, you predict that from there on it's going down. It's only going down. The only one that's still going up somewhat is the Permian. And it too is showing some signs of topping out. Let's look at US shale in the context of world oil. So this is by country. Everything below the black line is now in a state of decline. These sources are rather current, but you can see that actually world liquids have been increasing in recent years, and that's made possible only by US shale. So some people look at the situation, they say, oh, if US shale is peaking, then the world must be peaking. This is reinforced by the fact that over recent years, we're discovering only 1 barrel of oil for every 4 that we consume. So we're not finding new big fields. But future expert predictions of oil vary. This man, Art Berman, is very pessimistic. He has a colleague, Verberg, who monitors oil markets. She is pessimistic. This guy, Mark Mills, says there are hundreds of years of hydrocarbons left, mainly appealing to the innovation of the human brain. And this guy, Doomberg, he's a green chicken on his Zoom appearances. Oil is not really vital. We can get everything we need from natural gas. Compounding the problem is that even the experts don't know how much countries actually have, because each country wants to conceal how much it has. So it's very hard to tell. Now, the US Energy Information Administration is presumably following this, and I'm sort of relying on their prediction. These are predictions of coal, oils, liquids, and gas through 2050. And summarizing their predictions, it's flat. It's not growing, though, but it is flat. It's not catastrophically falling. But that's conclusion 1. Conclusion 2, the EIA does not foresee net zero by 2050. It's predicting rather flat consumption. I'll come back to that in a minute. Okay, now I want to think about these bigger questions. This is a little detour. We've seen that the economy scales with oil consumption. Let's imagine that cheap energy is flat. Then will the economy grow? And I ask you to consider, what does it take that you can go to the bank and put money in the bank and get $100 and get $103 in real terms next year? Very hard to get economists to answer this question. I have tried, but I think, using my astronomer intuition, that it must be that the economy is growing. If everybody can do this, somehow the aggregate economic production must be increasing. If the economy is flat or falling, will you get interest? Can you save? Can you save for pensions? Will Harvard continue to get many hundreds of millions of dollars a year from its staggeringly large $50 billion endowment, et cetera? Okay. What I'm saying is that financially, the future of oil could have huge ramifications, and therefore on the savings of each one of us. Yet another drag, which came along after I made this talk last spring, the looming demographic crisis. Population is shrinking, birth rate is falling, 1/3 replacement in Korea. China's population, many think, will shrink by 1/2, but you can't have a growing economy if your population has shrunk by 1/2. You have to have workers and you have to have consumers. So this is another trend that could actually cause world GDP to go down. All right. Chapter 4, electric vehicles, good or not? Here's some conclusions. The lifetime CO2 emissions of fully electric cars are comparable to hybrids and only 50% less than cars using conventional internal combustion engines. At the same time, though, the scarce mineral requirement is much, in my opinion, the total environmental impact much higher. With regard to trucks, turns out that you can't make electric trucks that are 18-wheelers because the batteries are too big. The whole cargo area would be batteries. And so here I'm giving you my opinion. The campaign to electrify cars and trucks is misplaced, and instead we should build smaller cars. We should improve internal combustion engines and aim for 100 miles per gallon in hybrid vehicles rather than build electric cars. Okay, some backup for this. The likely targets for electrification provide only 11% of total emissions. If we cut that by a factor of 2, we've saved 6% out of the total. Remember I said a while ago, don't be lulled into a false sense of security that somehow electrification of vehicles is going to solve the crisis. It is not. It is only a small part of the picture. Okay, here's a chart you can't read. The bottom line is that the emission intensity of an average patrol car in the United States is about twice as large as a fully electrified battery-driven vehicle. That's my factor of 2. Converting to EV saves only of order half the energy. And here is a recent study that shows that hybrids are actually just as energy efficient as fully electrified battery-driven cars. Okay? Long-haul trucks don't run well on batteries. Here's some statistics. Basically, with current battery technology, if you want to go however many miles we're doing, 1,000 miles, you're using a huge fraction of the cargo space. And they're hugely expensive. The cost of those trucks now is $375,000, and a regular truck is more like $200,000. People can't afford them. Okay, here's a summary of takeaway messages about batteries for semi-tractor trailers. I will not repeat. Okay, I've been concentrating on the CO2 footprint, but now let's look at the total vehicle and notice that the scarce mineral content of full battery EVs is much higher than conventional ICEs. ICEs are these black lines, and this is what it takes to build a typical battery-powered car. These batteries are using rare minerals, and you don't even see aluminum here. The cars need to be light because the batteries are heavy, and they use a lot more aluminum.
What is good graphite rare?
I don't know.
It's called.
Yeah, don't know. It's mine. That's all I can tell you. The materials in the car are one thing, but let's imagine the full system in which we've got these electric vehicles and we're charging them with so-called renewables. So renewable power plants also can use up a lot more of the scarce mineral content. So here's good old natural gas, wind, etc. So there's a double whammy here, and I'm going to return to some actual numbers for that in just a minute. And I just want to remind you that mining is bad, bad, bad. And willy-nilly consumption of these materials is very, very ill-advised. Modern mining is not green. Okay, there's some takeaway passages here, but I think I've already said it. And my opinion is that we should not be, that turning to electric vehicles is a strategic mistake. All right, chapter 5, power resources needed to actually achieve net zero. So here I refer you to this massive report number 42 by a guy in Finland, Simon Michaud, one of the people I've never met. And what he did was he examined 11 different uses of fossil fuels. He identified 8 of them as amenable to replacement with renewable energy. And he calculated the amount of new renewable energy that would be needed in order to achieve that replacement. And I'm quoting 2 aspects of his work. One, scenario A, which converted highway, rail, and maritime transport, all feasible energy transports. And the bottom line is that to achieve A, just this, requires increasing wind, solar by a factor of 5 and achieving all of these an increase of a factor of 15. So enormous increases in these renewable power plants. Here's the port. And here's the methodology, which I'm not going to go into in detail. It's predictable for any one thing like passenger cars. You start by counting the number of passenger cars in the world, how much energy they're using from gasoline, how much they would use if they had batteries, et cetera, et cetera. It's straightforward. It's a 1,000-page report, though. It's an incredible effort. What I do want to call attention to is that an assumption was made when he needs new renewable energy sources. He assumes that it is possible to simply scale up by some factor the existing sources. But it turns out the 2/3 of renewable sources are hydropower and nuclear power. And those basically are very, very hard to scale up in any meaningful way. So the net result is that his estimates are too optimistic. And I've tried to adjust them for that point. I don't know why he made that choice. Okay, so here's an example of a page, a table. Here are the 11 things. And these are the 8 things that he thinks he can deal with. There are 3 things that he can't deal with. Okay, here's an enlargement in case you're interested. Okay, so here's my point about the current mix of renewables. His assumed mix looks like this. These are wind and solar, and these are nuclear and hydro. So there's a big correction factor needed to his numbers if we think that that nuclear and hydro are not scalable. Okay, so here's scenario A. The entire highway, rail, and maritime fleets are now EVs. This is the portion of, well, this is all the renewables. These are the new renewables we need. And if we can't expand nuclear and hydro, then this little portion has to expand to this little portion, which is a total increase of a factor of 5 over what we have now. Okay, and here's the bigger challenge, all 11 categories. This is renewables now needs to expand to this large amount, and that's the factor of 15. Okay, so on paper, it looks for the moment that maybe that's possible, but there are some hard and truly impossible replacements in those 3 categories that he didn't address. Sorry, one of them is commercial airplanes. They can't fly on batteries. The trucks I've mentioned, and the only options there are to grow biodiesel. We will see that there's not enough to do that, and these sectors are going to have to shrink drastically. Light-duty vehicles looks feasible on paper, but we're going to see that it requires way more mineral resources than available, and no replacements are known for some items in the last category. So here's a pie diagram that summarizes these difficult to eliminate emissions. Cement, iron, and steel, load following electricity. To these, I would add making agricultural fertilizer and agriculture and mining powering machinery. Okay, so here are the 4 pillars of modern construction and food: plastics, steel, and cement. Let's examine them. Industrial uses of fossil fuels with no known replacements at this time: cement and steel making. These things require high temperature that you cannot get out of electricity. You really have to have the heat from fossil fuels. You can't make them from wood or nuclear power heat. They amount to 9% of all fossil fuel emissions. Making petrochemicals, you need temperature, but you also need feedstock. That's 4% of fossil fuel emissions. And now we come to agriculture. Agriculture is painful. The Green Revolution has doubled or tripled the output of acreage to make food, but at the same time, it's degrading the quality of soils. I read something recently that the carbon content, native carbon content in Iowa is only 1/3 to 1/2 of what it was 40 years or so ago before they started adding fertilizer. We're in a death spiral here. the productivity goes down, farmers compensate with short-term thinking, with more fertilizer, that degrades the soil even more, okay? So just imagine we waved a magic wand, Greta Thunberg gets her way, bingo, there are no more fossil fuels used. Half the world, maybe more, will shortly stop. Okay. Fortunately, we're not actually using that much fossil fuel to produce those fertilizers. So we probably could budget our use of fossil fuels to maintain this, but on the other hand, over time, we'd be further degrading the productivity of the land, which is not good. Green revolution is not green. Okay, here are some categories with potential replacements. Mining machinery, long distance trucking and airline aviation. Together, they sum to 9% of fossil fuel emissions. Let's grow bio fuels in order to fuel those important needs. Okay, so here's a chart that computes how much cropland you would need based on the current production of biofuels, which is small. We'd be scaling it up hugely by a factor of almost 13. Net result is, yes, I could service those aspects of the economy if I used all the world's cropland to grow biofuels. Not possible. And here's a slide that summarizes my numbers on biomass productivity. Okay, some people are enamored of using hydrogen to power, for example, long-distance trucks and or long-distance ships. There's a wonderful account by Alice Friedman in her book, Life After Fossil Fuels, about the problems with hydrogen. Hydrogen is dreadful. It's not naturally occurring, so we're only going to make it by putting energy in to dissociate water. And if we had abundant sources of energy, cheap energy, maybe we could do this, but energy is not going to be cheap in the future with these renewables. So the cost is out of sight. It also destroys materials, it leaks out of things, and it explodes. So I have not taken it seriously for a future energy source. Okay, now I want to say something I think that is new. Probably you've heard a lot about what I've been saying, but I think these points are new. There's a phase change that sets in to the electricity grid when solar and wind achieve a penetration of around 50%, 30 to 50%. So the modern grid is a miracle, and it provides high voltage stability and phase stability. That's something this is three-phase current. Voltage stability requires nimble power sources that can turn on and off to account for variable demand and supply. And natural gas is the source of choice in most electrical grids. Batteries could also do this. Okay, so this is a buffering problem on fairly short time scales a day. There's a longer buffering time that has to do with the fact that we have seasons here, and the sun comes and goes, and the wind blows or not on time scales of months. So in the Michaud study, he assumed a buffering time of 4 weeks. I'll tell you the bottom line here. If you buffer the productivity of a power plant by requiring yourself to save in a battery, adjacent battery, 4 weeks of power, at current battery costs, you have increased the cost of the plant by a factor of 10. And this is why I'm telling you that renewables are not cheap. Yes, the instantaneous point of production of energy is cheap, but by the time you take the whole landscape into account, they are not cheap. There's another problem. Phase stability requires a minimum mass of rotating generators. This is a back reaction. If one plant falls out of phase, Lenz's law from the phase coming in from the rest of the grid says, oh, you got to rotate faster, or you got to rotate slower. So there's so-called grid phase inertia, And that's the only reason the grid works and is able to maintain phase. So these renewable plants do not natively have that kind of phase information. You can supply it with some software, but still you need out there some phase reference, which people estimate is about 50% of the total production power. And so I've read a lot. I think it's fair to say that it's not known how we're going to operate a grid that is more than 50% wind and solar because of the phase problem. This was new to me. How am I doing time-wise? Need to move. Okay, I've told you about the electrical grid. This is typical time fluctuations daily in Ontario. This is an interesting slide. There are two numbers in every state. The upper number is the percent of solar. The lower number is the average cost of electricity. If you scan this, you will see that there is a rather good correlation. The more solar there is, the more expensive the electricity is. And here are some reasons why that is true. And California is definitely in that regime. Okay, this is my slide that says that from an actual study of California energy demand, with batteries, you would increase the cost of this particular energy installation by a factor of 20 running on solar. Okay, back to Michaud. Michaud tells us that the cost of power stations are 350 billion, but by the time we buffered them for 4 weeks, the total cost has gone up to 1.5 trillion. And both of his costs are too low by a factor of 15, because as I've said, he's made too optimistic assumptions about hydro and nuclear. Using his calculations, he compares the new mass needed to do what he just calculated with total global reserves. And you can see that in nickel, cobalt, lithium, and so on, we're talking about masses of metal that are far beyond what we even know is in the ground. This is something about battery storage showing that on the horizon, new battery technology will not change these conclusions. And here's a summary of hidden costs of wind and solar, but I think I've already said what is written here. Okay, very briefly, carbon capture and storage, two kinds. One is taking carbon dioxide out of power plant flues, and another is direct air capture. Both of these are central to IPCC pathways to achieve 1.5 degrees. And neither one is, they're both fantasies. The energy efficiency of carbon capture is very low. For example, in this actual plant, it was only capturing 11% of the total CO2 emissions. Doesn't work, and it's energy expensive. Okay, here are things that I haven't discussed in this talk for lack of time, and that's because I wanted to focus on the big picture items that contribute large fractions of the problem. Okay, I'm almost done. Extrapolating the blue line, well, now I'm an astronomer. I read lots of climate predictions. Frankly, I can't understand them. There are many different indices that are used to talk about carbon CO2 sensitivity. I can't understand it. So what I did in my simple astronomer way was something simple. Here is a historical graph. These light-colored lines show how the temperature has been varying based on cumulative carbon dioxide emissions by people. Okay, so all I did was put a blue line through that and assume, what I've done is I've assumed that our current rate of CO2 emissions this year will just persist unchanged. That's like the flat fossil fuel consumption that's predicted by the EIA, but I've extrapolated that to the end of the century, 2100. This is where we would be on this graph at that point, and I simply read off the temperature, 3.2 degrees of excess warming. Now, something you must know is that that's a planetary average, delta T. The land delta T is just about twice that. So if people talk about global warming of 3 degrees, what it means in Calcutta is 6 degrees. And it's centigrade, it's not Fahrenheit. Okay, so some people now have calculated human habitability niches for various warmings. This warming is 2.7 degrees. On my graph, that would be reached in 1980, not 2100. And the purple areas here are regions in which the annual average temperature is greater than 29 C, and that is a rough and ready threshold for where people can or cannot survive without air conditioning. So all of these purple areas would become, using my extrapolation, would become uninhabitable by the year 2080. And there are 2 billion people who live there. And the areas get larger quickly with small increases in temperature beyond that. Okay, a short word about economists. One Nobel Prize has been given to an economist for calculating climate damages. He estimates that at 2.7 degrees, the damage to the world economy is minus 2%. And yes, he does, William Nordhaus. And I invite you to contemplate whether or not he has properly captured the misery and distress that are going to be experienced by 2 billion people who have to move or die. Yeah.
So he claims that despite like a quarter of the world population,
yes,
survive because the economy become 25%.
Because he doesn't do this. Okay, he just looks at factories. Most of them are inside, so we don't have to worry. It's unbelievable. It's really unbelievable. Okay, so here are summary prospects for actually getting to net zero. I won't go through it because I've said it all. Just highlight the bottom. These would all be enormous changes, and we don't have the social incentives to make those changes. So we have a basic problem with our governance system. The capitalist economics has had its day, but its utility is over. Growth is over. Growth cannot continue. We have to have degrowth to have stability over time. And I highlight this somehow in this framework, the value of anything can only be expressed in dollars. So those 2 billion people have no value whatsoever. Taking aim at the United States, our democratic system of government cannot deal with slow rolling crises. You know, if we were attacked by the Chinese tomorrow, bingo, we would mobilize. But we're like the frog in the blender or the boiling pot of water. We just cannot respond for a whole bunch of reasons. And let me summarize my last point here. Our historic reverence for human life no longer fits the simply too many people. And so we have to confront that problem. And this is going to cause us, we need to develop a new vision for what human society is going to look like on Earth in coming centuries. Okay, so that's my last slide. And I promised to say a couple words about astronomers, because there are a lot of young astronomy students in this audience, and you may be feeling somewhat depressed. I would not, because I think astronomical training is it's unique. It's absolutely what the world needs to think about these problems. To wit, astronomers know that things can change. We know that there was a big bang with a temperature of 10 to the 28th degrees Kelvin, and the temperature of the universe today is 3. We know that there was a galaxy without our solar system. We know that early on, stars were metal poor and you couldn't make planets, and only later could you make it. It's built in. And the average person really has a very hard time envisioning that things could be drastically different. So that's one thing. The other thing I think that we're really good at is systems thinking. And we're very good at coming to conclusions with inadequate evidence. Right? And believe me, I think this is so important. We're quantitative and we can look at a graph and we say, well, this one's important. I need to worry about this. This one's a detail and so on. So I'm not sure, you young people, that you're going to be astronomers doing astronomy research for your whole career, but I would advise you to pay attention to what's happening in the world. Don't assume that you can just go to the grocery store and get food. Seriously. Don't assume that you'll have a stable society and the police will protect your home. Don't assume these things, but at the same time, stay aware and figure out how you can make an impact, because you can. Thank you.
Used for hybrid vehicles. I know you said it was really loud for all.
Oh, it's much less. Yeah, I mean, the battery in a full vehicle weighs hundreds of pounds and weighs about 20 pounds in a hybrid. It's like 1 mile versus 400 miles. Yeah.
What are your mind the largest or the most challenging aspects of exascaling nuclear we talked about? That is really difficult to scale.
Yeah, I'm really interested in nuclear, and I've been following that. And this guy on the Decouple podcast, it's just been a wonderful tutoring situation. He's Canadian. Canada has a lot of nuclear. Mainly, it's just the permitting process has been slow. We built very few nuclear plants. There are rather few companies in the world who can build nuclear and who can build it quickly and on time and on budget. And as long as natural gas is available, companies will, in coal, they will prefer to expand in that direction. Let me also say, I am worried about nuclear, though. I once was a big proponent, seemed obvious. But now I'm worried because if you take a really pessimistic view of societal stability and the ability of society to maintain expertise during social upheavals, all of those, there are 450 nuclear plants. Each one of them is a site of contamination, and it needs to be maintained by fossil fuel cooling. So what is going to happen to those? I'm not sure we should build more.
So we do have an online question. Dan, go ahead.
Oh, yeah, well, I was going to ask more about nuclear. First of all, it's obviously hasn't worked very well in this country lately to build more plants, and but it seems that's, well, one way to read what you have is that this is an overwhelming case for it that might sway opinion.
Yeah. Can I just say, you guys have read over the weekend that they're going to restart the remaining reactor at 3 Mile Island.
Oh, really?
Yes, the reason that's happening is because Microsoft sees a need for energy for data centers. So data centers, I didn't even mention data centers looming as another requirement for more energy. But
Do you think that, what, do you have any opinion about fusion?
Not really. It's just that one's mind is focused by the year 2050. And
Oh, yeah.
developing a new nuclear, which is thorium, for which the basic principles are known. People say with these complicated plants, it takes decades for them to become real. So I think fusion is out of sight. And besides, I don't think the answer to the problem is having large amounts of cheap energy, which allows us to maintain this inflated level of economic activity. I think we need to think about getting smaller.
Do you want to pick or should I?
You.
Okay.
Any kind of time scale estimate if battery technology were to improve so that they could be used in like 18 years and things, like how long would it take for batteries to be?
I'm not a battery expert. I did meet a young lady who is doing battery research at Berkeley. I met her a few months ago. And she was talking about improvements of a factor of 2. And that's meaningful, obviously, in the numbers that we're talking about. So factors of 2 would help, but I don't think even at that level would basically change the arithmetic that renewables would still be way more expensive than whatever available coal and oil we have. I think we're driven to use whatever that cheap energy is as long as it exists.
Yeah, I wanted to focus on that underlying bit there, too many people, because your original premise of GDP correlating with energy use, I'm sure that's true, but really we should look at both of those per capita. And because, to zeroth order, you add another person, then you add more of both. And then at the same time, I want to, say if we just cut the population in half, of course, global emissions would go down roughly by a half.
Mhm.
And I know people who are older than me haven't really thought about this, but people who are my age or younger have thought about the next generations. In 2100, probably none of us will be alive, maybe a handful, but future generations of us will. And so, I mean, I commute by bike. I'm a pescatarian. I do a lot of the things that are good that I can do on my own. But the best thing I've done is I haven't had any children. Because I mean, really, like if you have 2 children, then you are just adding on to global emissions. You're adding on to GDP too. So I'm just curious of your thought about that without, I don't think that there should be any like government mandates or anything like that, but just this
I do.
okay. But this overall idea that, I think when you talk to young people, they're scared even to have children because of these issues.
And that's probably figuring into this drop worldwide. People are also worrying about endocrine disruptors because insects are fertility is down, mammalian, all fertility in animals is down across the world, and that doesn't have anything to do with volition. That has more to do with capability. So I'm not going to answer your question, but I do think it gets at something that's really important, and that is if we could make a model of some future world, let's imagine we bridged this coming crisis. How would we like to live? I myself am not a proponent of living in a tent. I would like, if I broke my leg, which I did recently, I would like to be able to go and get some modern medical care, and etc. So I think we can live with a lot less energy per person. I think we should try to figure out what is sustainable energy supply for the world, decide on what the energy consumption is per person, divide, and that tells you what the future world population would be. At least having that number in front of us would be instructive.
So it sounds like you're quite pessimistic about a democratic government being able to.
I am, yes.
So are you in favor of an autocratic government instead, or any other kind of government that could help us out of this?
I think at the moment, our leaders are not free to say what's in their minds or even think these thoughts. I think primarily that is because they are thinking about getting reelected. And I think they think that way because getting reelected is expensive. And that makes them trapped and beholden to the same corporate interests. I mean, have you noticed nothing really changes whether we have Republicans or Democrats in office?
Just wait.
Huh? Just wait. No, but seriously, these campaign contributions come in to equally to all kinds of candidates. It's impossible to get people thinking differently. So what I would do, I think, is finance all campaigns out of public funds, make them much shorter, much more intense, and see how that works. And maybe there would be more people who would be feel the power and courage to speak up and speak truth.
You said that there's not really enough or maybe any societal incentives to make these changes. And I guess I was wondering what whether you see the societal incentives being to be made in policy or like through movements, or like what pathways do you see forward to make societal incentives like more?
Well, everybody who's thought about this says to first order, we need a carbon tax. And carbon needs to be really expensive. And that's at a level of, to have a real dent in people's consumption, gasoline has to get twice, 3, 4, maybe 5 times as expensive, as an example.
So that would be, sorry, just a quick follow-up, that would be like, that would be great, but those things aren't necessarily happening quickly or happening with this whole political system that we're just talking about now.
That's right.
With funding and how it's,
Yeah,
like how campaigns are, so like, I guess I'm more asking about like the pathways to that.
I'm very pessimistic.
Yeah.
Okay, I don't have a good answer to your question. And I think that, you know, if we were to go outside right now, we look around the campus, it's beautiful. What could be wrong? You know, it hasn't come home yet. And it has to come home. And people in a democracy, they have to feel pain, real pain, but by then it might be too late. That's the problem. We have 2 different timescales. So I can't answer your question, sorry.
One thing you mentioned is meat, the consumption of meat, which I'm no expert at this, but a lot of experts say went up to 20%, maybe let's even say it was half of that. That's something that we actually could change
Yes,
very easily.
yes,
But it wasn't included. I just thought I should mention that it wasn't included in any of your.
yeah. I thank you. That would have been a good thing to put on those things, topics not discussed. Yes.
I know that you're a proponent of biofuels. I was just wondering.
Am I?
I mean, I thought that's what you said on like 2 slides back.
No, I said that that they're very inefficient. We're not going to solve those problems with biofuels.
That's fair.
Okay,
I mean, that was my question. That was like, how efficient are biofuels comparatively?
in terms of CO2 footprint, they are actually about half of a coal-fired power plant. Whereas wind and solar would be 1/20.
Yeah, you mentioned this earlier, but I was wondering if you can elaborate a little bit more on this deep well. It seems in your talk, there's this underlying idea throughout all of it that Ralph is really seems to be at a natural condition that relies on the availability of ground priced energy, right? And I wonder about how would an economy that is degrowing work, given all the difficulties you also outlined, right?
I think
thoughts about that with one particular thing, because it seems that what we are doing right now, instead of pointing to a situation like that and making it work, is putting a lot of emphasis in finding a new source of cheap energy and thinking that maybe AI can do it, right?
exactly.
And so there's so much hype and effort into making AI work because we believe that magically, maybe, which will thankfully, that will find new sources of energy that would allow it to sustain the growth of the economy. But yeah, what are your thoughts on that, if you can elaborate?
Okay, well, I'm not an energy expert. I don't know how to structure an economy with different forms of energy. But so I can't answer your question, but will instead say that, you know, I took aim at universities in my talk. I think there are some key questions that actually the collective expertise in universities might be able to address, and this is one. And so what I'd like to do in the next year is go around and talk to some people, maybe you can help me with this, and identify roughly a dozen key questions that universities should be thinking about, like the carrying capacity question is one of them, and how to restructure an economy with different forms of energy and how to transition, which is really your question. So we need models and simulations of these things, and I don't see anybody doing that. Certainly not in economics departments. So I think, great question. I don't know the answer.
Okay, we're out of time officially, but I encourage you all to sign up for one-on-one meetings with Sandy today. There is a schedule circulated. Let's thank Sandy again.
Okay.